And then the positive voltage below the threshold means depletion. And then the positive voltage above the threshold means inversion. Okay, so let's do some derivation here through the band diagram. So here again, this is the structure, and this is the band diagram, and this is a flat band condition where you have the phi m equals to phi s, and here is the equilibrium state. You don't apply external voltage, gate voltage equals to 0. So then, as we discussed, here the metal side, this is the metal side, the Fermi level, and then the silicon side, the Fermi level, this is p-type. Okay, so there will be lambda. This is the flat, and then we have this phi b. That is distance between the EI to the Fermi level. So this is the starting point, and now we will apply positive voltage. So if you apply positive voltage to the gate, as we discussed, we are going to push down, right? This Fermi level of the metal will be pushed down. Positive voltage pushed down. So then the band of the oxide and the semiconductor here will be bent because this is down here. So you need to push down all of them. So now the band becomes a blue curve. This is when you have the gate voltage larger than 0. Then we will define a few terms here. So the band bending from here to here is called the phi s. There's another phi s here. This is called the surface potential. This surface potential describes the band bending at the surface of the EC. This is the band bending. At the surface. Because to the very bulk of the semiconductor, this is a very substrate. Then this is flat. But at the surface, you see the blue curve here. Then this EC is bent down by this amount. And this is called the phi s, surface potential. This phi s is important, as we will use that to derive some equations in the next. Okay, so let's look at this. So by the way, so this depletion region starts where the band starts bending. So then this here we talk about depletion region is from the surface to where the band starts bending. So that distance W is the width of the depletion. Alright, so then let's look at this. So this is a structure, and when you apply positive voltage, gate voltage, then initially you will have the Na minus, that is the depletion charge, with this depletion width. So let's draw the charge density along this direction. So the charge density, of course, when you apply positive voltage to the gate, the metal surface will accumulate the positive charge. So you have positive charge here. And then the Na minus is a fixed charge by the acceptor. And then here the density of the dopant is Na, and it's minus. So that's why we draw the charge density negative. Here, if this is 0, then this is negative, Na minus. And then let's multiply by Q, that is a charge. Q is a charge quantity, constant. So it's QNA, that is the negative charge. So this negative charge in total will balance the positive charge here. And then what is the total negative charge? It's QNA times W, because you have W here. The density is Na, but you need to multiply if you consider one-dimensional charge quantity in total. Then you need to apply this one-dimensional length, which is the W here. So this is total charge here. And the second parameter here is the electric field in this structure. Will be something like this. Will be something like this. So why is this? So this is because from the charge you can get the electric field. This is called the Poisson equation. Poisson equation. I don't know, in your college physics, like the EM lectures on the electromagnetism, there's the Maxwell equations, and one of that is Poisson equation. So basically it says that if you integrate the charge over some volume, you're going to get the electric field in that volume, because the electric field is introduced by the charge. You have positive charge, then the positive charge will emit electric field. So if you do the integration of the charge, you will get the electric field. So then you will get this. For the field here, yes. And then you have the oxide field, EOX, here. So the electric field in the semiconductor is decreasing. The reason is that because here you have a constant charge doping. If you integrate the constant, then you get a linear function. So that's why you get a linear ES here. And then this is from charge to the field. And then the next is the field to the voltage. It's one more integration. This is one integration. This is another integration. Because you know the field over some distance will build up that potential. So if you do the field integrated with that distance, you will get the voltage potential. So if you do that, then you get this kind of curve. So this is the gate voltage you apply, some positive voltage, and this voltage will drop across the oxide and the semiconductor. So if you apply gate voltage, part of the voltage drop on the oxide, part of the voltage drop on the semiconductor. Eventually you go to 0. That's the ground. So then the gate voltage will have this kind of linear shape here, dropping across the oxide, and then some parabolic function in the semiconductor. This is because we will integrate the linear function, the first order, you're going to get a second order term here. And then here in the oxide, because it's a constant, if you integrate, you will get a linear function here. So that's why you have the linear drop, and then the second order kind of curvature here. This is first order and then second order. And then if you do this, then you can get the phi s, because phi s is this one. So the voltage on the structure, gate voltage, part of voltage drop on the oxide, part of voltage drop on the semiconductor, and then the voltage drop on the semiconductor is the surface potential here. So how much is this surface potential? So you need to integrate the electric field over this distance W. But the electric field is changing here, it's not a constant. So let's take an average here, which is half of the electric field. We need to do half, because let's take an average, it's changing from this value to this value. So let's use the half of the ES to integrate over this distance. It's like you are doing this, and if you use half of that, then you will get the same thing. If you do integration, that means the area under that function, right? If you do integration, so you can use a middle point and multiply by the W, you can get the area. When I talk about integration, that means you count the area under that function. So if you do that, then here this will be half epsilon 0, epsilon silicon, and then multiply by the W, and then you can plug in this Q total here. So if you do everything, then you get this one. So by the way, I don't require this derivation, so it's very complicated. But I want you to understand the relationship from the charge to the electric field. So it's to integrate the charge over some distance, you will get the electric field. From the electric field to the voltage, you integrate that field across that distance, you get the voltage potential. Okay, so if we do this, then we'll get the surface potential, phi s equals to this equation here, QNA W squared divided by 2 epsilon 0 and epsilon silicon. So epsilon 0 is the, the permittivity of the vacuum, and epsilon silicon is the relative permittivity or the dielectric constant of the silicon, which is unit means for silicon is around 4. Okay, so then this is what we have, the phi s from the previous slide. And then if we back calculate what is W, you can do this way, right? If you want to back calculate using the phi s, then you move terms around and then take the square root, you will get W equals to the square root, and then you 2 epsilon 0, epsilon silicon, and phi s. So we will just back calculate W from the phi s, then you get this one. So that means the W is proportional to the square root of the phi s. So then here we derive so many equations. The eventual goal here is to derive the threshold voltage, because that is very important. So what is the threshold voltage? So threshold voltage is the voltage you apply to the gate. That is the gate voltage. And the gate voltage, as we discussed, has two components. One is the voltage drop on the oxide. One is the voltage drop on the semiconductor. So it's this VOX plus this phi s. And what is VOX? So VOX will be the Q total over the COX, because the charge over the capacitance will give you the voltage. So what is the Q total? Q total in this case is the total charge here. This charge is across some capacitance of the COX, because here is a capacitance. So then this charge over this capacitance will give you this voltage drop, VOX. So here the VOX is the total charge, which is QNAW, over the capacitance of the oxide, which is COX. And then plus phi s. So here we plug in the W to this equation here. We get the W as a function of phi s. So we replace the W with the phi s. So you get this one. Okay, eventually we get the gate voltage as a function of the phi s. Why we care about this? Because as we discussed 2 slides before, when you have the inversion, you need to move down the band by 2 phi d. That means here you need to bend down this by 2 phi d. That means phi s equals to 2 phi d. That is the condition for the inversion. So here we are going to plug in the condition for the inversion, which is phi s equals to 2 phi d. So you plug in here and plug in here. So eventually, you are going to get this equation. And this equation is the threshold voltage V threshold equals to this square root of this term divided by COX plus 2 phi d. So after this long journey, eventually you get that equation. That equation is for the threshold voltage. And here we can also get the maximum depletion width, because as the threshold voltage phi s equals to 2 phi d, we can plug into this 2 epsilon 0 epsilon silicon 2 phi d divided by Q on A. That is the maximum depletion width. This is at the inversion condition. And above the inversion, let's say you have more electrons, then the depletion width will not increase anymore. So, any questions?
Can you explain again what exactly phi represents?
Explain the phi b?
Just in general.
Phi s?
Phi b, phi s, phi d. Like, what does the phi represent? What is it?
So the phi s, let's do this one more time. Phi s is the bending of the band at the surface. So here you see as a substrate, or let's say in this substrate here, this is p-type, right? But the surface now become n-type, because the EC is moved down from here to here by this phi s. EC moved down from here to here, so the surface become n-type. And we call this bending of the band at the surface, as the surface potential phi s. And if we move to earlier slide here, this tells you to change from p-type to n-type. You see the Fermi level here now becomes Fermi level here. That means you need to move down the EC by this 2 phi b. That's why we have that conclusion phi s is to be 2 phi b to get that inversion. Because this is the n-type surface, right? This is a p-type substrate. This is what we draw in this figure. This is the substrate, so it's a p-type. And this is surface, it's n-type, and you have this inversion. So then the EC needs to be bent down by 2 phi b. So that's why this phi s equals to 2 phi b. Any other questions? So I know it's a little bit tricky, so I want you to review maybe the recorded lecture video after class, and also read the complementary textbook. Question?
What is the bottom variable on the threshold voltage?
Bottom variable, you mean the
Is that C?
COX?
Yeah, is that C oxide?
C oxide, that is the capacitance per unit area. And that is actually the COX is the epsilon oxide, epsilon 0 and epsilon oxide, divided by the thickness of the oxide. So that means here if you have the MOS, you have the thickness, EOX, and if this oxide material has the EOX, then you will get the COX. That depends on the thickness of that oxide. Alright. So here again, I just copied from the textbook. We have the VOX and phi s. Then you have the phi s plus VOX. So you get this one, and then you plug in the W. So you will get this eventual equation. And this VFB in our previous discussion is 0 because we assume the phi m equals to the phi s, that flat band condition. That means without voltage, your Fermi level of the metal equals to your Fermi level of the semiconductor. So the VFB equals to 0. If this is not 0, then you have that one added to the threshold voltage. But in this class, I think we don't discuss that condition. So we'll assume the VFB equals to 0. So, all right, any questions? If no, then we can stop here today.